We're very excited to have you all here, and welcome to our first Flink Druid meetup. And we're going to go ahead and get started. I'm going to do a little intro to the Flink community, and then we're going to have Peter here talk to us about Druid. So we're going to get right into this right away. So let me know. You should be able to see my slides here. Everyone seeing that all right? All right. Great. Excellent. Good to hear that. Good to see you all in the chat as well. All right. So as I said, I'm going to give a little intro to the Flink part. Peter's going to give us some updates on Druid. So I come from the Flink side of things, so I'm going to be covering where Flink fits in here. So first, I will introduce myself, and then I'll introduce Apache Flink as a technology, focusing on the highlights, what's relevant for interacting with Druid to get you set up for Peter's next talk, and some best practices. Then I'll talk a little bit about our users, our community, and our use cases, which should also give you a little bit more foundation of all the ways in which Flink and Druid work really well together. Hint, we have a lot of very similar use cases. And then lastly, we'll have some info on where to go next there. And after this, Peter will give you all the info you need to get started with Flink and Druid. So hello, my name is Kato Schur, and I'm a developer advocate. And I first got started with stream processing in 2017 when I was a software engineer at a large data analytics company. My team built that company's first stream processing data pipeline using Apache Flink. And I first got to know my current coworkers when I became a regular speaker at their conferences, and then I got totally hooked once I got to know the open source community around it. So I work at Viverica, which is a Berlin-based tech company that built and maintains the open source project Apache Flink, as well as a related integrated platform. The Viverica platform enables organizations of any size to derive immediate insight from their data and serves internal and external stakeholders in that way. And it's done by streamlining deployments and other operations and providing in-depth analytics. I live in Portland, Oregon in the US. Of course, I had to represent with our famous PDX carpet there. And in my free time, I do woodworking, dance, and appreciating terrible puns. So I'm seeing a lot of familiar faces in the guest list here. So for those of you who are already familiar with Flink, hi, first, it is very good to see you. And secondly, I'll try to make this part short for you, or at least very relevant to the topic at hand. However, for those of you who are not familiar with Flink, I do want to introduce kind of what we do and get you a little bit caught up and up to speed here. So I won't be covering things like general stream processing concepts. So if you are unfamiliar with streaming, I can provide resources to you at the end. I also won't get super in depth on how Flink works, and I'll try to keep the concepts that I do cover related to the topic that we have here today, related to how it works with Druid and how Flink fits into the larger ecosystem of tools and everything there. So what is Flink? Although Flink is now has unified batch and streaming capabilities, it is foremost known for being a stateful stream processing engine. This is my favorite part, is the rough translation of the word Flink in German means nimble. So really highlighting the flexibility and the speed of that framework. It is a particularly flexible and complex framework that was built to solve many software problems, particularly in the areas of real-time and big data processing. However, it was also built to address many of the common challenges that come with stream processing, namely being able to provide features like high availability, various other safeguards, and exactly once guarantees, which I'll get to in a moment. And all of this while maintaining high performance, low latency, and scalability for each of these features. It is also highly customizable, so it can be used for a wide variety of specialized cases. The most common cases, though, are data pipelines, particularly for fraud and anomaly detection, where data needs to be extremely precise and accessible in as near real time as possible, and where it often requires a lot of complex transformations and to have that all done very quickly. So before I go into the mechanics of that, a bit more on what Flink solves there. So Flink's strength is in its scalability. As I said, it's high performance. So for instance, computations done at in-memory speed, which is pretty cool. And various features like those exactly once guarantees, I mention a lot because it's my favorite feature, and robust high availability options that allow for those high levels of data accuracy and reliability. Additionally, there's this ever-growing ecosystem around Flink of libraries, connectors, other features and partnerships with complementary tools like Druid, and software that have enabled it to fit into a wide variety of different use cases and pre-existing systems. And a big shout out to our awesome open source community for making a lot of this happen. So specifically, it can be run on all cluster environments, such as Hadoop, Yarn, Mesos, Kubernetes. It can also be set up to run as a standalone cluster. And Flink's timing and state features allow even further flexibility for what kinds of applications the runtime can be run on. So let's say you're working on a project that needs to be able to scale up and down rapidly and needs to be reliably distributed. Maybe you're doing something like anomaly detection. You need that data to be accurate, accessible in real time, or you're doing machine learning, or another situation where maybe you can just access your data whenever, like no problem, but you're dealing with such mass amounts of data and doing complex transformations on that data and modifications that if you had to wait for all of that to go through your data pipeline in start and stop batches, or even just using a simpler stream processing engine, that would be kind of a pain. So again, the main problems that Flink is really solving for are situations where you need that real-time streaming capability for really big amounts of data. And then, as I said, it also addresses some of those inherent stream processing problems. So stream processing can be challenging. So some are more obvious than others. At the most basic level, you have unbounded streams of data. It doesn't stop, or at least it shouldn't. If it does, you've got other problems. So, when you can just sit and process data, if there's an issue, you can resolve it during a pause or just keep things paused. You're not likely to have to deal with back pressure, data piling up, et cetera. Additionally, since most of the benefits of stream processing are that it can handle such huge amounts of data and push through a pipeline at such lightning speed, that means that if you're doing stream processing, you're probably doing it to take advantage of those benefits, because why not? So then you have all of those inherent challenges as well. You also could be ingesting from multiple sources, maybe joining streams. These streams might be coming in completely different formats, and you're trying to merge those together as you're ingesting them. So you just have this potential for a much more complex system in a lot of ways, which is a good thing, but it means it's more complicated. So this can often show up in storage issues, data loss or duplication issues, and the need for a different type of failure recovery since, if you're losing data, it's from the whole stream and not just from a little batch. So good news, Flink is set up to take care of a lot of these things by default, but a huge amount of Flink is also configurable. So there's a lot of options to cover things like storage or back pressure in a way that will best suit your needs. But that's kind of a long description, and most of that is actually pretty easy to see. We have a lot of different examples of config docs. That's not really worth me spending the time on, so I will provide resources at the end for that. The one thing I do really want to emphasize, though, is the failure recovery and data accuracy. I think this is where Flink really shines and has some really unique features around. So during a failure, if it's batch processing or a simpler stream processing app, there's these very well-defined options for how to reread data that was not being read while the app was not running. No kidding. But with stream processing, there not only needs to be a way to address this, there needs to be multiple ways of addressing it because you want to cover all the different use cases. There needs to be different ways of handling data that could be preferable over others. So for example, a lot of people choose stream processing for especially really high-powered streaming engines like Flink for its speed and consistency. And if getting data fast with low latency is more important than getting all the data, then at most once processing is a better choice because it dictates the data will just be dropped in case of a restart or after a failure, and then the app will just start running. Or it might be more important to get all the data, but it doesn't matter if some events are duplicated. So in that case, at least once processing is going to make more sense, where if the app fails, it'll reread the last window of events, which ensures that everything is accounted for. But of course, some events could be read in twice. So the last and most complicated situation is where it's equally critical that the events are read in quickly and consistently, and that all events are ingested, and that there are no duplicates. So this option is referred to as exactly once guarantee, and it has a reputation for being difficult to enable in other stream processing frameworks. So this is a question I get a lot about Flink because people say, oh, okay, haha, you have exactly once, so do these other ones. Is it actually exactly once? Or people are used to it not actually being that precise or that accurate. So I'll go into a little bit, but I definitely encourage you to read the docs on this. There's so much there, and this is my favorite feature. It's pretty cool. So as I said, there's several streaming frameworks that do it. They're all implemented very differently. And the biggest thing is they perform differently once you scale up. So I've seen a lot of people do proof of concepts for Flink versus some other streaming engines, and you see it all start looking the same. And as soon as you add more and more data in there, you're going to get drastically different performance. So this is the super lightning round of one of the things that kind of helps this work is that this is made possible through Flink's unique checkpointing and save pointing system. So Flink is able to address a lot of these issues in how it does the checkpointing and save pointing and how it handles state management. So those combined are kind of how we, very high level, how we set up our exactly once. So checkpoints are a mechanism that copies the current state of each task after all the tasks have processed the same input. So by default, only one checkpoint can be in progress at a time, but that you can configure it to have more too, if you want. Checkpoints are primarily used in failure recovery. So when there's an app failure or there's a network disconnection or killed process, there's mechanisms to restart the whole app. And then before the tasks are started again, they're reset to that last completed checkpoint. So after a restart, the app will ingest and process all events between the failure and the checkpoint. And the beauty of this mechanism is that because the tasks are reset to the checkpoint, any data that occurred after that checkpoint is essentially dropped and reread, which means you still get that exactly once guarantee. The data gets in and read, and there will be no duplicates. So this diagram, is very simple and kind of makes the whole process look very simple. So again, this is all paired with how we handle the state management, and that's how we're able to get that really high performance for this concept. So there's also a lot of confusion about save points versus checkpoints. So I always like to have a little slide about that. So save points are very similar to checkpoints. The main difference is that they're implemented differently and they typically contain added metadata. I also kind of like best practice PSA. I do sometimes see people switch how they use both of these. So I really like this little rubric just to remember what they're kind of both for. So as for the implementation, checkpoints are created, loaded, and removed automatically by the Flink framework. Save points, however, have to be generated manually and are not cleaned up. So therefore, it's important to make sure save points get deleted. It's best practice not to delete them before another save point or checkpoint has completed, or else, you could lose data. So that's always a good PSA too. I think most people are pretty good at that though. And there's some automation in there as well now. So because save points contain at least some of the data that a checkpoint has, they can be used to restart the app, but that's not really what they're for. So I always remember the difference here is that save points are for isolated intentional situations, as opposed to being a fail-safe preventative mechanism, because that is what checkpoints are for. Also, if you switch them, it's not the worst thing you can do, but the way that how much data that they store, you could use up more memory and things. So that's some of the reasons to make sure you are using them for the correct purposes. Situations that are appropriate for save points are ones like archiving the current state, scaling the application up or down, migrating the app to a new cluster, running A/B tests, pretty much any scenario that includes modification to the application, configurations, or the application logic. So checkpointing is particularly important because it addresses the main challenge of Flink being distributed. So again, that's a problem, or it's a challenge that often comes with distributed systems and stream processing. So this is how Flink addresses that, and that its state is only maintained locally. Checkpointing is handled and stored with Flink's state backend. This mechanism does the local state management and stores checkpoints or pointers to a checkpoint to remote, and all of that two-way remote and persistent storage, like a database or file system. And then checkpointing is handled differently depending on what state backend you're using. So I also don't tend to go into exactly how checkpointing works, because it's going to look totally different for all your different state backends, and there's a bunch of options. So another aspect that's kind of core to this is state. So state is not relevant for every stream processing framework, so it's very important to talk about with Flink, because that's going to look different than the other ones. So state contains information about the data, like count of how many events there are. And with Flink, state can be read from and written to by the operators of a Flink application, where it's also read and stored as the data progresses through the app. So kind of that whole system. When state is not kept, then processing a particular event does not depend on any other prior event processing, and everything can be done independent of each other or the order of arrival. So that's a situation that is more straightforward, but you don't get the fault tolerance. So in a restart, in that kind of situation, which is not us, the application that does not save state can just continue from where it was before the restart. Again, that's typically what you see in batch processing and some of the less powerful like streaming engines. So when an application is stateful, you want to make sure that since you're continuously ingesting data, it's also being saved as state. The size can grow exponentially. That can be expensive, cause memory issues. So having fail safes for that is very important. So we really value having those kind of fail safes at Flink, and making sure that we have high availability recovery options. So the biggest benefits are that stateful applications are more fault tolerant in case of failure. There's more robust options for modifying or evolving the application, performing A/B tests with different versions, or updating the app version itself. As for storage, Flink can save state and other outputs to various different external storage, like Apache Hadoop file system, HDFS, or Amazon S3. And then for the local state, it's on the JVM heap or on like a disk like RocksDB. And the state access is at memory and disk speed. So it is like hyper fast. So that's pretty cool. And it's only limited by your heap or disk size. Okay, so that was a lot. So bringing this back to kind of the main building blocks, especially since Flink is so complex, it can be easy to just continue to use the same features and miss out on some of the newer things being developed. So I always like to bring it back to this, because if you've been working in one section of Flink, there is so much there. It can be easy to really kind of just stay in that one area and not see some of the new things. So as a Flink user, Flink gives you different APIs to choose from that trade off ease and expressiveness. So the higher level, you have APIs like SQL, which I'll get into in a moment, the table API and PyFlink that are all closer to the relational way of thinking about data. These APIs allow you to express problems in a very concise way, and they do all the operational heavy lifting for you. As you progress down, using the APIs gets more complex, but you also get more and more control over the programs you're building and how they're executed. So when you reach the core building blocks, it's pretty limitless what you can do at the bottom there. So in the interest of time, I'm not going to get into this too much, but I want to give a special shout out to Flink SQL. If you haven't tried it yet, I highly recommend it. It's been the component that I have personally had the most fun with, and it's a really great way to get other people using Flink who may not be experts. So back when I was an engineer, this was really, this would have been really exciting. We actually didn't have this back then, but we constantly had people trying to use Flink who were not Java or Scala experts, who are more on the DevOps side. And this really, it's language agnostic, and it has all of the access to Flink's, all the powerful, flexible things about Flink in a SQL client. So it's super easy to use. I also really like it as a way to sketch out proof of concepts. So because you have access to Flink, you can just rapid fire make a bunch of different proofs of concepts for various different things and systems that you want to build. So again, it really helps simplify a lot of that complexity. The main benefits here, as I said, you get access to all of the benefits of Flink. You're not really like limited there. It's particularly useful for getting the unified batch and streaming option for distributed systems. Users can focus on the business logic and not on the implementation details. And along with the fact that it's just SQL, I mean, not under the hood, but from the user's perspective, as I said, you don't need to be Java or Scala experts, and you don't have to worry about switching all your code over. So it's just super lightweight and gives you a lot more autonomy. In the real world, we see a lot of use cases here in building unified pipelines for offline and offline model training, independently building end-to-end streaming analytics pipelines without having to depend on an engineering or operations team that's specific to Flink or whatever, and more easily generates features for machine learning model training. So we do see a lot of machine learning cases in there. So in a nutshell, it gives you this high-level relational-like way to query data streams using language that you're probably already kind of familiar with. So the difference between running SQL on top of the streaming engine. So in your regular database, so this is like a regular one, where you execute your query at a certain point in time, the engine takes a snapshot of the table at the time the query was run, and then computes the results based on that static snapshot. Then the query terminates. In streaming SQL, the query is continuous. So again, this is what's all going on under the hood. The UI, basically the SQL client, is going to look basically the same. So in the streaming scenario, you first deploy your query, and then whatever data is added to the table, the changes are continuously ingested, and the results are also continuously updated. So the query just keeps on running and never finishes until you cancel the job. So keeping up with the theme of simplicity, this is an example of sessionizing a click stream and count on number of clicks per session, just a random example. The left-hand side is using the data stream API with Flink versus using Flink SQL. It's doing the exact same thing. It's just like, makes it so much more simple. So with Flink's other APIs, queries are still dependent on a table program written in either Java or Scala, and has dependencies on build tools for submitting the cluster, whereas the Flink SQL client, all writing, debugging, submitting any sort of table programs to a Flink cluster is just done. So that's all done under the hood. Plus you get your visualizations on the command line. I don't have it in this talk because I have several other whole talks on Flink SQL, but you get this lovely gigantic squirrel in addition to your regular visualizations. So, you know, spoilers. All right. So I know we're getting a little low on time here. So in summary, the real-time power of Flink, it pairs very nicely with Druid for this reason. So having that real-time processing, being able to provide unified batch and streaming solution is also a really great way to leverage, again, that relationship between Flink and Druid. And just having that stateful processing, treating state like a first-class citizen, distributed state snapshots, and those exactly once guarantees for fault tolerance, flexible APIs, and our ultra high performance, which of course is fun. I'm going to just go kind of quick through these next ones since again we got a little bit of a late start today. I do want to show a little bit about how Flink starts up. So I'm not going to get into, I had a bunch here for like what goes on in the background, kind of what happens with the job managers and how those interact with your external resource managers and everything. There's some great docs on that. So if you are interested in that, I can talk to you about it afterward or send you the resources. Basically, we have on top here what the Flink UI looks like right out of the box. And then we have our Verica platform. So that's going to make things a lot easier if you're streamlining your deployments and having a little bit more analytics in there as well. So that just kind of further abstracts that out. So those are two options. There's also a community version of the Verica platform that you can test out. And if you want to get a really well-rounded start, I would recommend, obviously going to the docs, but checking out our social media, our YouTube accounts, specifically our conference talks. So additionally, we have hands-on training sessions a couple times a year. It's run by David, our trainer, who is amazing. I've taken some of his trainings. They're really great. He's always updating them with cool new stuff. We also have some self-paced trainings. And then Flink also has one of the most active mailing lists in the Apache Foundation. So if you want help from a really engaged community, I definitely recommend checking it out. We also have several mailing lists depending on kind of what you're either looking for help with or looking to get involved in. We're going to go through this pretty fast, but use cases. Flink is primarily used for event-driven applications, data analytics applications, data pipeline applications. We have some really awesome customers, really awesome users here. This is, again, going to go super fast because of time, but our event-driven applications typically includes things like fraud detection, anomaly detection, rule-based alerting, business process monitoring, web applications like social networks, things like that. All of these diagrams are also in our docs. So if you want to look at these in more detail, I know this is kind of a lot here on the slides, you can check out those. So data analytics applications, typically this is like quality monitoring for like telecommunication, analysis of product updates, ad hoc analysis of live data, large scale graph analysis, things like this. Data pipelines, this is kind of like where my background comes from. So real-time search index building, like e-commerce is really huge here, and continuous ETL in e-commerce. So with all that, where to go next? We already talked about ways that you can contribute and get involved. Honestly, the best way to do that, in my opinion, is Flink Forward. It's this super awesome conference. We're finally doing it in person again this year, which is super exciting. Kay here has done an incredible job organizing it. It's going to be in San Francisco in early August. If you scan that QR code, that'll bring you to the site. We are also still accepting talks. And then we are also hiring, so you can check that out as well. And with that, thank you so much. Huge thank you to all the attendees. It's so good to see some new faces, some familiar faces. Thank you very much to Peter. I'm very excited to hear your talk. And thanks to Apache Druid and Flink and our amazing event organizers today. There was a lot of work that went into putting this on. So yeah, thank you there.
Great, thank you.
Yeah.
Thanks, Kato. So now we're going to move on to Apache Druid, which will be taken by Peter Marshall.
Okay. Cool. Hi, thank you, Kato. That was really cool talk. I've got so many questions for you, but I think maybe we should meet instead. And then I can ask you lots of questions. You just repeat, as I go through the talk today, if anybody wants to ask anything, please do just put the questions into the chat and I'll answer them at the end of the session. So, okay, there will be some overlap, I think, but I hope it prompts more discussion. It's always good for Apache communities to come together. So I'm really glad that I've got the chance to speak to you guys today as just being a member and a participant in the Druid community. So it's lovely to meet you all. Okay, who am I? So this good-looking chap, that's me. My name is Peter Marshall. I'm Director of Developer Relations. I work in the customer success part of Imply. We get a lot of freedom to work very closely with the whole of the Apache Druid community. We're active in the channels, doing meetups and talks like this. So do come and say hi. My contact details are at the bottom there. Yeah. I suppose the only interesting thing on this slide is that I buy books and I never read any of them. Oh, and I have a theology degree, but please don't ask me any questions about God today. Okay, so this talk is called Upstream Processing, for modern analytics. And particularly, I'm focusing on those kind of use cases where in the Druid community, people are using Flink alongside it. You will see the logos of other technologies which are also available, but I'm obviously interested in Flink today. It's in 4 parts, so we're going to look at the modern analytics ecosystem. We're going to look at where Druid fits into that pipeline, which is segue. Thanks, Cato. I also got to look at some like real world examples of those architectures, but I want to get through that really quickly because what I want to focus on is those places where if you're using Apache Druid or thinking about using Apache Druid, some places where some form of upstream processing is important to keep the data flowing. So let's start with this wonderful picture of a geyser, I think is how you pronounce it. Because this is how I visualize a modern analytics application, the kind of really cool stuff that's coming out of Silicon Valley now. These geysers work because this water that sat on the surface, maybe on a lake, get it? It's working its way down into the planet. It's about 2,000 meters down where you get these extremely hot rocks and this water fizzes and it boils. And then there's this massive exothermic, hydrothermic reaction that pushes the water right up into the air. And it's not just like a little dribble of water. This is a proper spectacle. And these are the things that we're trying to build now with our new technologies like Flink and Druid. These are like really awe-inspiring applications. They're the kind of applications where users will see and they'll hear and they'll feel the analytics that they're doing. These are true spectacles. So what are some qualities of these kind of applications that you might build nowadays? Well, they're very fun to use. So they're not like the kind of thing that I grew up with, because I'm 45, which was really, really dull and boring and you had to be a specialist. No, these are really cool interactive applications. They're very personal, they're very intuitive. And because they are, they're extremely popular and they're going to get used by a lot of people. In fact, some people have built applications using Druid as a backend that they thought was used by a few. You've got 10,000 users. Thirdly, they aren't just about real-time data, although real-time data is obviously really cool. Real-time data is about immediate warnings. It's about immediate risks and immediate threats. But we can't all just live based on threats all the time. We have to have historical data in there as well, the data that we can think about, that we can consider really carefully. So with Druid, we're able to put both of these things together and present them inside an application. And that means that when people are using these kinds of applications, they're making decisions really quickly that are impactful within the business, decisions that steer companies towards long-term success. And Citrix is one of those users. This really helpful URL, I really need to shorten that, is a video by Aaron Janarthanam at Citrix. And he said that work is no longer a place. What does he mean by that? Well, I take this as meaning that they know how to write data spectacles. They know about those application features. They've created something that's really awesome. And with this particular application called Citrix Analytics, they've created what I call knowledge societies. So decision-making isn't something that's made just by one person or by one small team. It's very participatory. It's very collaborative. That sounds a lot like the Apache way for me, so I'm quite happy with that. So what about the database that sits behind this application? Here's some qualities of an application database that you'll need for this front end. It needs to be able to maximize the kinds of questions we can ask the database. It mustn't have a fixed schema or a fixed data cube. We obviously need some good APIs. We also need lots of storage space. It needs to be able to scale very easily. It has to deal with these tons and tons of, we're going to get to it. Its data, it needs to have a good cost benefit balance by doing things like tiering the data and prioritizing the queries. it needs to have high availability, it needs to optimize, all this cool stuff. And of course, what's the database for that? I'm going to say Apache Druid is obviously the database for that. But there is a job that we all need to do as data engineers in building an application like that. We need to deliver the right data, we need to deliver it at the right time, and we have to understand how each of these components are going to work together, which is one of the reasons I'm very happy to be here today, to kind of give you an idea of what people are doing. So let's build up this generic model for a pipeline where we've got Druid sat as the analytics database. So on the left-hand side, we've got our producers, that's the fuel. And in the middle, I'm going to put all these components that people are using to get the data to the desk. And then on the right-hand side, we've got the user interface. That's the amazing data spectacle we're going to create. So this is a quote from one of the original developers of Druid, almost 10 years ago now. His name is Fanjing Yang. He's actually our CEO at Imply. And he says that typically Druid sits after your data lake or message bus, and it provides the analytics engine that powers applications with sub-second statistical calculations, combining real-time and historical data. So in this pattern, Apache Druid is the database that we're going to use to power the presentation layer, because it allows for interactive conversations, it allows for high concurrency, it allows that combined view of real-time and historical data, and it has this capacity for zero-time kinds of applications that people are building. So what can Druid connect to? So it can connect to streaming sources like Kinesis and Kafka, or any Kafka. And also Druid instance if you wanted to do something mad like that. What about at the presentation layer? So these are the kinds of things that we see people plugging into Druid. So they might be building something custom, say with React.js or with Angular, or they might be plugging in a desktop app that already has Druid support built in. So things like Metabase, and especially our open source cousins in Superset. And of course, Imply has its own tool called Pivot. Or you might be doing some kind of data science tooling. So Grafana or Jupyter or Zeppelin. But what's creating all the data out there in the community? Well, tons of things. So telemetry emitters, log files, APIs, all sorts of event data are going to go into our pipeline. But as we all know, data is never exactly in the way that we want it. And even when it eventually is in the way that we want it, someone will ask us to do something completely different with it. So we do need to do some kind of interception on this pipeline on the way to Druid. We might create separate data sources. We might just update what's already in that data source. So for Druid and for Druid users, there's a key phrase that I use, and it's statistically ready. What that means is that we've treated the data in a way that makes it easy for people to use that application and to make decisions based on it. Now, there is a gap on this slide, and it's at the bottom right-hand corner, because there is also people who actually use the data within Druid to do things. So it was really interesting to hear about use cases around anomaly detection, for example, because when any processing that requires windowed aggregations, Druid is very good to enable quite flexible exploration of that statistical data from Druid and do it very rapidly rather than going to the source data. But that's a different talk. So why is this important? Well, we have to get the data and we have to transport it properly, and not just any old data, but data that is focused on delivering this next generation of applications. We're not talking about things that are done for monthly reports. We're talking about data that has to be propelled at speed so people can make really meaningful decisions and explore the data on their own terms. We're not therefore talking about a data lake that we look at once an hour and maybe we'll add some numbers up. We need something in the middle here, some processing engine that will take that data, process it reliably and consistently, excellent, and then move on and pass the data on to the presentation layer. And there's going to be hundreds of thousands, millions, billions of events an hour flying through this ecosystem. And this is important to get because this data is life-changing. It gets into people's brains, it gets into how they feel, and it helps them think about what they're passionate about. And that's why in the Flink community, it's really important to me in the Druid community that you understand the passion that people have when they're using Druid. We need an engine that can help this flow of statistics-ready data through to that modern analytics application and do it without delay. And it's not the same as sticking everything in a data lake. If you want to read more about how Druid works with other technologies, there is a Druid forum at druidforum.org. You can log in there, register for free, and there's a tag browser up at the top right-hand corner. So some technology or data format that you're working with, there are articles written by members of the community. You can just go and have a look at that and see how they're using it. So where does Druid live? Well, Druid lives in this last mile to the desk. And I think it's an essential part of any ecosystem where you're trying to build those kind of applications, where delays are really not acceptable, where latency needs to be really low. And that means we need to have those processing engines and those event hubs further upstream that will propel the data. That's why you've got Airbnb using it and Twitch using it and Zscaler using it, because of the speed of decision making that's required. So let's have a look at what some of these architectures look like. Now, this one's back from 2017. It was written by the International Journal of Engineering Research in Computer Science and Engineering. You can go and Google this, but they were using it to look at anomaly detection. And you can see here in the middle, they've got Druid after a beam-controlled Flink processor. I think that's the right wording to use. This is Netflix's architecture. So here they've got Kafka being read by Flink, some processing happening. It's chucking it into S3 in iceberg format, which I still haven't played around with, but need to. And then they've got Spark doing some stuff. But then they've got two databases that they're using for the actual analytics work that the end users are doing. They've got Trino and they've got Druid. But notice that there's this very important line here that goes direct from Kafka into Druid. So they're actually picking up the live events immediately and surfacing those to the end users. And to kind of make this distinction even clearer, Parth said recently in an interview that Druid is Netflix's choice for anything where the end user is waiting for a response. If they're sat there and they've asked a question and they want to know immediately, that's when they're using Druid. For everything else, they're using other databases like Trino. They might even they might be using Elastic for other types of searches. This is another good example of this. So this is Lyft, again, where they've got Flink integrated, this time pulling data out of Kinesis. So they have the kind of the fast lane, which is where Druid is sitting. Flink is actually dropping again Druid's line, where they're chucking Parquet into a bucket and then Presto's reading that. And that's where they're doing the more complicated queries, the things that take longer to run. And they also have Hive in there, just for good measure. If you want to hear more about that, there is a talk called Enabling Real-Time Querying Using Druid, Flink, and Kafka, which is really, really good video to watch, where they distinguish between the two very quickly. Okay, so that's real-world examples. Now then, let's get to some technical things. And every single one of these things that I'm going to show you is a talk in itself. So if anybody has any questions, then please come and send me an email or come into the Druid channels, say hi, peter.marshall@imply.io, and I will give you more information. So what could we do upstream of Druid that will help Druid out? So first of all, you can be a source for the data, shock horror, that's very important. Secondly, is about laying out the data for the way that Druid does its distributed ingestion. You can also spend some time harmonizing the schemas that you have in the source data with what the end users actually need, because Druid is not a data lake. You might need to do something to make the schemas better. And also front loading some processing that otherwise would be done at query time. So on the left-hand side, I'm going to step through a generic SQL query, and we're going to fill that with memorable moments of surprise and intrigue. On the right-hand side, I'm going to just outline some areas that functionality you can use in Druid, all available in the docs. You can have a look at that, and then highlight some jobs that you might do upstream in the bright orange box there at the top right-hand corner. So when it comes to selecting the actual dimensions, in Druid, when you ingest data, you can specify which dimensions you want to put into the table. You can specifically exclude dimensions, or you can also just let Druid get on with it and automatically create the schema based on the data you've provided it. But upstream, you might choose to do that trimming work, if that's the right word to say, to give it the right width in the number of fields that are available, doing that somewhere upstream. I mean, if you look at this data here, for example, it might be that the users think that they need to know the number of noses that each person has, and they might think that in order to do a count distinct, they need visitor and car registration. But as data analysts and data engineers will look at this and go, well, actually, knowing what the end users are going to ask, I don't need all of that. And doing that exercise and doing it on an ongoing basis is really important for end users who are using applications based on Druid. So IronSource have a very large Druid deployment out in Israel, and they spend a lot of time and effort maintaining schemas. And by doing that, they've reduced their query latency by nearly 75%. And I guess what I'm really saying here is listen to the end users, ask them what they want, keep an eye on it, and be what we all know as agile and users in mind. So when I'm designing a schema for Druid, I will quite often look through the queries, and I encourage everybody to do that anyway, for whatever database you're using, to work out what the end users want. But I look at the select, I look at the where, the group by, the order by, I look at the calculations and the aggregations. And at this kind of scale, it's important to talk to them about the cost benefit of storing all of that data, of filtering all that data at the scales that we're operating at with these kind of applications. And again, remember that Druid is not a data lake. When it comes to expressions that we might use, in Druid, I can actually query, in the SQL, I can use expressions in the query, which is really great. But I can also front load those expressions at ingestion time in what's called the transform spec. Now, upstream, I might actually perform those calculations so Druid doesn't have to. It's a question of cost, really. Do I want to spend money doing a select clause which has a calculation between Fahrenheit and Celsius with every single query that's going to execute on Druid? Or because that calculation is never going to change, do I do it at in time or processing upstream? Now, this is a stupid example because calculating between Celsius and Fahrenheit is not a very expensive and complicated function to do, but you might have one in mind that is more complicated. And you have to ask yourself, is that calculation going to be a burden on my presentation layer database in Apache Druid? These are the kinds of functions you can carry out at ingestion time, or in fact at query time with Druid. So you can look at conditions, arrays, time, math and string functions, regular expressions. You can also do a lookup between a key and a value, and you can also extend it, and you can also write JavaScript, although that's probably not the best way of doing it. Have a look at the docs there if you want to read more, but this is really important to look at the queries and ask which ones of my queries can I actually front load a lot of the work for. And one of the very common use cases for this is by using the conditions to add new dimensions to enable us to do funnel analysis. So for example, one of the things that might happen at ingestion time in Druid is on the actions data in Clickstream. And here what I've done is I've used an if statement to just work out whether or not something signifies an impression or a click or a conversion. And then because Druid is really, really fast at doing some operations, it means that I don't have to do this at query time over and over again. I can just use a sum function, and it's extremely fast to do it that way. Another approach is to enrich not the click data, but the session data. And this is definitely something that is very important to know. So sessions aren't unique to marketing. They're also used in video streaming analytics and web behavioral analytics. They're even used in manufacturing. So in this version, we take the session level data and we've worked out what the last stage was that someone got to in the funnel. Now, again, because Druid is extremely fast at group by operations, I can group by last stage and then reverse count in order to create my funnel on the presentation layer. That's a great approach because it also means I can support not just funnels, sides. Then I just update the logic upstream to create the correct deduction on the right-hand side. That kind of preloading of effort that would be done at query time also applies to what are called lookups, that is value lookup things you can do within Druid. So here's a good example. Let's say I have a key, which is my HTTP status code, and I want to dereference that to a value, let's say a nice friendly description. Now I can do that at query time using Druid SQL, but no one is going to change the meaning of HTTP status codes anytime soon. So really I should front load that and do that at ingestion time. But remember what we were saying about functions? You might actually choose to do this in the processing engine, especially if that kind of value is going to be more valuable in other areas of your ecosystem. So now let's talk to the where clauses. So the where clauses in Druid make use of secondary indexes. And now secondary indexes is something that is a differentiator between Druid and, say, a query engine that's running on a data lake. And they're used in a very effective way in Druid to execute where clauses. So I can also apply a filter at ingestion time. But upstream, again, maybe I'll choose to create a dedicated source for the data, which is going to be filtering out all of that stuff for me. Why is that important? Well, I might build a very focused user interface where someone is only looking at 500 HTTP server areas, and maybe there's 5 billion events a minute coming into this application. Or maybe they only want to know about suspect transactions. Now I can apply that filter at ingestion time in Druid and create a table that only contains those rows. That's much leaner, it's much more cost effective, and it's a ton faster when queries execute. But remember, if you apply that Druid will read every single message from the stream and that will accept it or reject it. So if only one of those 7 billion rows matches the filter, Druid still needs to have the power to read all of them, even if you only want just one row. So it may make sense for you to do something upstream to give Druid a much purer, leaner source of data, so it doesn't have to have that much power. I think it also goes without saying that if Druid doesn't do what you need it to in terms of filtering, like some complex sampling rules or something like that, you are going to have to look at extensions or do something upstream. So if this appeals to you, do please go and have a look at the transformation spec filtering to see if it will allow you to do what you want it to do. Oh, I missed my pretty picture of my bird. Damn. Also, Druid does pruning that is essentially free. It does that based on time. That's why time is such an important element of any Druid query. Druid data is sharded by time first into segment files. And the broker, which is the thing that handles all the query processing, distributes work only to those nodes in a Druid cluster where that time period is being held. And it can dramatically, therefore, reduce the amount of energy that Druid expends in getting answers to queries. But Druid also has sub-partitioning. So I could pick a particular dimension, let's say, where someone has got an indicator of a tenant ID, perhaps. And I can sub-partition by that data. And that's also used Druid during the Druid pruning process. Sorry. Okay. I think we can skip that one. If you do use in filters a lot in Druid, by the way, please do go and look at Bloom filters. This is just a very clever way of handling ins with approximation. Also, it's important to think about the sources of data that you're actually going to query from your end user application. In Druid, there are some areas of configuration that are distinct to each of the tables. For example, retention periods. Perhaps you have a security policy where you need to logically separate the different data sets. You can also apply your tiering rules based on a time for each table. Your tasks are managed, they have affinity, they're replicated based on a table, and also have this thing called auto-compaction, which is to do with defragmenting the data, especially on late arriving or out of order data, is a very important feature. So it might be that you choose to employ some kind of processing upstream, maybe you'll bifurcate or something upstream, so that Druid knows that that particular source, which is destined for that particular table, is complying with those particular information management requirements or levels of completeness. Another really important feature of Druid, and it's again to do with this kind of pre-processing before querying, is that Druid can do time-based roll-up or summarization of data. What that enables me to do is to take some kind of aggregates that would normally be computed at query time over and over again, and to actually compute them at ingestion time. So it reduces the number of rows that are actually going to be stored inside Druid, which is good for money. And it also reduces the overall scan time. So you get a massive improvement in performance. And there are some use cases, though, where you need to do those aggregations based on something other than time. And for those use cases, again, you might need to do that upstream. Do go and have a look at that feature, really important, called rollup inside Druid, so you can understand how that works. And related to rollup is approximation. If you haven't looked at Apache data sketches yet, I genuinely believe it's probably one of the most important inventions in computer science in decades, I would say. And it enables us to do approximate count distinct and set operations and quantiles, using approximation. And it's not as horrific as you might sound. We're not talking about errors of like 50%. We're talking about errors of like 2-3%. In what you store in kilobytes of what you would normally store in gigabytes. Really, really important. If you are looking at doing count distinct and theta sketches and quantiles, set operations and quantiles, do go and look at Apache data sketches. They can be generated by Druid at ingestion time, but similarly, you might need to generate data sketches that are not just time-based. Maybe a data sketch will contain all of the people who visited your website in a particular cohort, and you want to be able to use that data sketch to do a kind of an in statement or an and statement with data that you've got inside Druid. Again, another talk. And then there are joins. Now, Druid, in its queries, likes you to select from one table currently. And that's because the join operation happens inside what we call the execution pyramid, right at the very top, where resources are highly constrained. So we don't particularly like subqueries, we don't particularly like joins currently because of that. However, there is a new development in Druid, which was announced, I think, at Druid Summit last year. So instead of having a scatter-gather architecture, which has these limitations, it will be much more like a mesh. But currently, you do definitely need to think about doing something upstream to denormalize the data or to do some complicated join operations before the stuff hits Druid. And bonus, if you're doing anything complicated with especially things like lag and lead, you may need to do that before Druid. State is important. Druid is not a state store. It isn't a place where you can update rows every 5 seconds. It's not an OLTP. So if you need to maintain state, maybe the current state of an order or of a video streaming session, that might need to be done somewhere else. There is an entire talk on that. And finally, it's really great that Cato mentioned sessions, because session analysis is really important on a whole range of different topics. And there is this model, which again, I'll have to go into another time, called the Delta Event Model, which is what will allow people to do real-time analytics on the session data, even though it's not ready yet because the session hasn't finished. And that's one of the important things about every application built on top of Druid. And that is that people access the data and they can talk to the data as quickly as possible to make the decisions that they need to make. So this is a very important design for us in the Druid community, because it helps us create session analytics, hopefully brilliantly. Oh, sorry, there's one and finally, and that's this brilliant eye. Please remember, if you do implement Druid, it is part of your entire pipeline. It's part of the entire ecosystem. Don't just monitor your connectivity and your throughput and correctness, something about management and capacity management and release and deployment, etc. So this is my final slide. I've said finally 3 times now. This is my final slide. Think about wide and narrow sources for different use cases. Think about where you're going to do those calculations to front load queries. Think about short and long sources by using filtering. Think about splitting your sources according to different information management requirements. Definitely investigate rollup, and definitely go and have a look at Apache data sketches to see if you can use approximation. Denormalize and enrich upstream, but as I mentioned, that will become less important when the new query engine gets put in. Definitely look at doing stuff that's very complicated around windowing upstream, and remember that Druid is not a state engine. And yes, I think that's me. If you want to get involved, please go and have a look at the Druid project page. There's a GitHub, awesome. And if you want to learn more about Druid, there is an implied training program, free to register, learn.io, and there's a course on where you work through some live labs with actually deploying Druid and then actually using Druid live to do ingestions, and it goes through those modeling principles we just covered today. That was very quick. I do apologize for my speed, but I hope that was useful. Thank you, everybody.
Thank you so much, Peter. Is there any questions before we close off for the day? I know we're slightly over time, but just gonna hold tight for just one moment to see if anyone's got anything come through. Perfect. All right. Thank you, everyone. Good evening, good night, good morning, wherever you are in the world today. Thank you so much for joining, and hope to catch you on the next one. And be sure to catch on the YouTube live stream at Viverica Data. We'll have that live stream put on there so you can catch all the highlights from today's talk. Thanks so much for joining, everyone. See you.